if we are finding the pH or concentration of strong acids, if your concentration is 1 molar, then you know that your H plus concentration is 1 molar, and the pH is going to be negative log of 1. That's a no-brainer because HCl is strong and there's no equilibrium, and we know that all of the H in HCl is going to dissociate and be H plus in solution. It's the same for strong bases. If KOH is 1 molar, then OH minus is 1 molar, and the POH is negative log of 1, and that's that. But when you have a weak acid or weak base, to calculate the acid-base concentration, or pH, you need to use the Ka and Kb, and you also need to do a Rice table. This relationship here is actually one that you want to keep in mind, because if you're given the Ka but you have a base, or you're given the Kb and have an acid, and you need the other one, you can use Kw to go from one to the other. So if you need Kb, you just take Kw, which is always a constant, divided by whatever Ka you have, and you get Kb, and vice versa. So it's just good to know. All right, we have HCN, and we have a 1.1 molar solution, and we're given the Ka. So I'm going to see if I can fit this all here. First, I have to write the equation out. So I'm going to throw it in water. So I have HCN plus H2O. It's an acid, so I'm going to get Cn minus plus H3O plus. It's 0.1 molar. H2O is a liquid, and so I just put an X there. Like I don't care, I don't need anything there. It's just an X. And then this is 0, 0 because we haven't started yet. So this is going to be my change row, negative X plus X plus X. And then my equilibrium row is 0.1 minus X, X, and X. Please notice that my Kas are always really small. And so since they are small, I can ignore this little minus X. So when I write my Ka expression, it's going to be X squared over 0.1. Okay? I'm going to say 4.9 times 10 to the minus 10 times 0.1, and I'm going to square root it to get X. All right, I had to bring 0.1 up, and then I had to square root because X was squared. And so X is going to be 7.6 times 10 to the minus 6 molar. Well, X is what H3O plus is, right? So what I just found is my H3O plus concentration, or my H plus concentration. Okay, so find X, and now you have your concentration of acid. So now I can just take negative log of that and find my pH, which I'm going to actually do up here. So I'm going to take pH equals negative log of my hydrogen ion concentration, which I just found to be 7.6 times 10 to the minus 6. And if you do that out, you get 5.15. That's my pH of a 0.1 molar solution of HCN. The Rice tables are always pretty easy, and the math is too, because these numbers are really small. All right, I want you guys to try 12. Okay, 2.02 is your pH. Use the Ka, use the Rice table to figure it out, and there you go. Number 13, we have 2 Kb values, and we need to figure out which base is stronger. So we just compare the Kb's. So you look for the larger Kb value, which is for this guy, methylamine. And so that's a stronger base than ammonia, because that's a bigger number than this one. Okay. NH3. I'm going to use the space above to solve for this one, and then I'll use the space below because I didn't give myself a whole lot of room. So I'm going to write out my equation. I throw in my base with water, Oh my goodness. All right, this is a base. NH3 is a base, so it's going to accept a proton. So that makes NH4 plus, right? Because it accepted that hydrogen, and OH minus. So I made a strong base. That's what you're supposed to do. All right, so 0.1, nothing, 0, 0. Minus x plus x plus x, 0.1 minus x, and x. KB, I'm given KB, and that's going to be x squared over 0.1. So I take 1.8 times 10 to the minus 5 times 0.1 and take the square root in order to get x. So my x is 0.0013. X is my hydrogen ion concentration because I'm dealing with a base this time. So my X will be the concentration of OH minus. So if I need the pH, I got to go from OH minus to pH. So there's a couple things you can do. I'm going to first find the POH and then just subtract because that just seems the easiest way to do it. Just don't forget that you have to do this with bases. All right, so my POH ends up coming out to be 2.87, but that's not my pH. My pH is going to be 14 minus 2.87, which is 11.13, and that is my pH. Just don't forget that last step. Once you find the POH, then you have to subtract from 14. All right, try the next one. Okay, I think the biggest issue with this problem is knowing how to write your chemical equation. So anytime you have a nitrogen containing base, that hydrogen's always going to go on the nitrogen. So then the CH3 is just going to stay there. He's just there for the ride. The nitrogen is what is accepting that hydrogen from the water. And so that hydrogen's always going to go onto the nitrogen and it will then have a positive charge. So we've gone from NH2 to NH3 plus. And then once I get my Rice table, I have x squared over 0.033 equals KB. I'm given the KB right here. I find x. X is my OH minus concentration. Find my POH. And then I subtract from 14 to get my pH, which I have here. So 16 is if you have to go the other way, where you have the pH and you have to find Ka. So what we want to do first is find the concentration from pH. So we got to go the other way, and then we can solve for our Ka. So I'm going to solve 16 here, just to show you. So we have just a generic acid, who cares? I'm going to write out my equation. We have 0.1, 0, 0, minus x plus x plus x. And then we have 0.1 minus x. We can always omit the x with acids. So you're good. You don't have to worry about it. All right. So I need to find what x is. Remember that H plus is equal to x. And if I want to find H plus from my pH, I'm going to take inverse log, which is 10 to the, right? And then you take 10 to the minus 4.25. And that's going to give me x. So that's 5.62 times 10 to the minus 5. So that's my x. So now I know that Ka is equal to x squared over 0.1. I just solve for K. 0.1 minus 5.62 times 10 to the minus 5 is essentially 0.1. So I'm just going to leave it. And so when I solve, my Ka is 3.16 times 10 to the minus 8. No units. So you just got to kind of work backwards. Okay, try 17. There you go. There's your Ka. You're just going to work backwards. Remember that 10 to the is your inverse log. So you gotta press second and then your log button. And then negative pH. So there's that. Okay, we need to determine if an ion is going to be acidic or basic in water. So the idea is you throw one of these anions, we're going to talk about anions first, in water, and you need to determine if that anion will make the water acidic or basic. Okay? So you need to think about, when you have an anion, you need to think about what acid it came from. Because all those anions were going to pair with a hydrogen. So I'm going to just write on the other side what the acid was. Okay. If this acid was a strong acid, like the first one, what that means is that your Cl minus that's now in solution is not going to go back to HCl, right? Because the whole idea of a strong acid is that it irreversibly reacts, right? And so that Cl minus is going to stay Cl minus and it's not going to go back in water. It's going to be neutral. Nothing happens. Oh my gosh, my writing's terrible. If that acid was weak, well, your anion is your conjugate base. It's a weak base. It's going to make, so if the anion came from a weak acid, it's going to make the solution basic. So this is strong. HNO3 is strong, which means that this is going to be neutral. Okay. So we get to classify each anion as a weak base or pH neutral. So this one we know came from HNO3, which is strong, so it's pH neutral. All right, you guys, pause and do the rest. NO2 comes from a weak acid, which is nitrous acid. So NO2 minus is the weak base itself. Because NO2, when you throw it in water, it forms a basic solution because it takes that hydrogen back. It forms a weak acid, but it also makes a strong base. And so that kind of takes over. Okay, we have acetate ion makes acetic acid. That's weak. So your acetate ion is a weak base. SO4 2- sulfate makes sulfuric acid, which is strong, and therefore it's pH neutral. All right, so the opposite goes for cations. Ammonium was ammonia. This guy ethylamine. Okay, so these guys all came from weak bases. If you had, let's say, sodium, so that would have come from sodium hydroxide, which is strong. So this one would be your pH neutral. The rest of these are weak acids because the bases were weak bases. Same idea. This was calcium hydroxide, so it's pH neutral because that's strong. This was weak, so it's weakly acidic. This one was weak, so this is also a weak acid. All right, so let's put this all together. If you have a salt, you're going to have an anion and cation together. So what you need to do is take them apart and figure out where they came from. So I say, like, look at the parents. So for sodium, the parent base was sodium hydroxide, which is strong. So we can ignore Na because it's neutral. They're not going to come back together in solution. So it's just a strong base, and that's that. There's no equilibrium there. HCl also comes from a strong parent. Cl minus comes from a strong parent, HCl. Strong acid, so chlorine is neutral and can be ignored. And by can be ignored, I mean that it's not going to change the pH of water because it's not going to form an acid or a base. It's just going to hang out as sodium and chlorine. It's not going to combine with water to form anything. They're just going to hang out and do nothing. So overall, this would be a neutral salt because both of them just sit there and do nothing. So other neutral salts would be like KCl, lithium bromide. All of these would have come from strong parents. So these are all neutral salts. Okay. So now we have to take these apart. So let's look at A. I'm going to take it apart. So I have Na plus and I have F minus. So Na we know came from a strong base since that was NaOH. That's neutral. And there's no change in pH. But now we have an anion that came from a weak acid. So it's acting like a weak base, and so this is a basic salt. And so overall, this is a basic salt. The sodium's neutral, it does nothing, but the F minus was a weak acid. It forms a strong base in solution, so it's going to be basic. I'm going to do one more and then you can do the other two. All right, K plus, that came from KOH, which is strong, so this guy's neutral. NO2 came from HNO2, which is nitrous acid, which is a weak acid, which means this guy's acting as a weak base. Overall, basic salt. All right, break these last couple apart. All right. This guy, we have two neutrals because K plus is KOH is the parent. SO4 is sulfate, and sulfuric acid is the parent, which is strong. So they both come from strong parents, so they're both neutral, and overall it's a neutral salt. You break up this one, we have ammonium and chloride. Chloride comes from HCl, so we know that's a strong parent, so it's neutral. NH4 acts as an acid. NH4 plus, ammonium is acidic, so we have an acidic salt. Okay, that's how to tell whether your salt is basic or acidic. What if you have two weak, so we have F minus, C5, H5, and H. All right, so these both came from weak parents. Then how do you tell if it's acidic or basic? You have to look at the Ka and the Kb. So this one is a weak base, so that would be the Kb and the Ka, and determine which one's stronger. I'm not going to have you do that, but I always have someone who's worried about getting two that are weak. So if you do, you would just compare Ka or Kb. And same goes for this guy, right? They're both... Oh, they both actually have the same. So this one, they have the same Ka and Kb. So this would be neutral because they cancel each other out. But that's a special case. But anyways, that's how you would tell. And there you have it. Okay, polyproducts are super easy. They all have more than one hydrogen out in front. So you just got to break it down. and take one off at a time. So I'm going to do A. So you're just going to throw this in water. All right, we're going to get rid of one hydrogen. That hydrogen's going to come here. Okay, so there's one. And then you have to do it again. So here's our other ionization reaction. Throw it again in water and have it react one more time. Okay. So we have acid, base, conjugate base, and then that conjugate base turns into an acid for the second one, reacts with water, conjugate acid, conjugate base. So you're going to have as many equations here as you have hydrogens. So try B and C, and I think that's it. All right, so there's B and C. Make sure it makes sense. Don't forget your charges. Each time you take a hydrogen off, that negative charge gets a little bit bigger. And there you have it. All right, and that's it. I'm going to skip the last two because we're not going to cover that. All right.